All right, so we're going to review the second derivative test. Now, you guys know that the second derivative we can use to test for concavity and can find points of inflection. But your second derivative test is actually going to help you find your relative minimums and maximums, your relative extremas. All right, so let's look at a function. If I give you a little sketch of a function, here's my relative max. Here's my relative minimum. Okay, what the second derivative test says is if you take the second derivative and you take your critical number and you plug it into your second derivative, if you get a negative number, you have a relative maximum. Likewise, if you take the second derivative, you take your critical number and you get a positive number when you plug it into the second derivative, you have a relative minimum. And then the only unfortunate thing is if you take your critical number and you plug it into your second derivative and you get 0, your test is going to fail. And when your test fails, you have to go back to using the first derivative test, which is a little annoying because the second derivative cuts out us actually setting up our intervals and testing. Our second derivative says plug the actual critical value in or critical number in and look at its sign, not the intervals on which the critical value separates the x-axis. All right, so let's take a function. F of x is equal to negative 3x to the 5th plus 5x to the 3rd. All right, so I'm going to take the first derivative because I need to find my critical numbers. Okay, setting the first derivative equal to 0, I can take out a negative 15x squared. I get x squared minus 1. Set them both equal to 0. I get 0 and plus and minus 1. Those are my critical values. So if I were to go ahead and now use the first derivative test, I would have to put these 3 values on the number line. I would have to break it up into intervals. I would have to test the intervals and see if it was increasing to decreasing or decreasing to increasing, and then determine the relative minimums and maximums. Here, I can go directly to finding the second derivative. I get negative 60x to the 3rd plus 30x. Now, I don't need intervals. I'm actually going to plug in the actual critical numbers that I got. And I'm going to check out the signs I get when I plug them in. All right, so negative 60 times negative 1 to the 3rd plus 30 times negative 1. All right, negative times negative is positive, so this whole thing is positive. So because I get a positive number, it's opposite of what you think. It's a relative minimum. Okay, next, plug in 0. I get 0, so the test fails. Okay, plugging in 1. I get negative 60 minus 30, which is negative. So I have a relative max. Okay, now I'm going to still plug back into my original function to find the actual relative minimums and maximums. Now, just to not make this video completely too long to watch, if you do take a couple minutes and you perform the first derivative test on 0, 0, you're going to find that 0, 0 is not a relative minimum or maximum. So this one, you'd have to go ahead and use the first derivative test. So put it on the number line and separate the number line on 2 intervals, negative infinity to 0 and then 0 to positive infinity. And you're going to find that it won't change from increasing to decreasing or decreasing to increasing. So 0 is not a relative minimum or maximum. All right, let's finish it up. So I need the actual point. So now I'm plugging back into the original function. So f of negative 1 is negative 3 times negative 1 to the 5th plus 5 times negative 1 to the 3rd. This is negative times positive. I'm sorry, negative times negative is positive. This becomes negative. So my relative minimum is -1, comma, -2. Okay, this is nothing. And then my relative maximum, I'm going to plug in 1 into my original function. So -3 times 1 to the 5th plus 5 times 1 to the 3rd. So this is -3 plus 5 is 2. So this is 1, comma, 2. So this does cut up a lot of time, especially if you don't have one of the values fail on the second derivative. Because this value never failed on the second derivative, we would have been done in just these few steps, which is much less than using the first derivative.